Okay, so last week we started chapter 9 about the differential equations. So we started with a model the population of the virus in a container. So we use this PT, the population at time t. And the hypothesis is PT is proportional. So we use this for proportional. So it's the change of the population, proportional to the population. But our first model is the more virus we have, the faster the population grows. We have an equation. The proportional, so the derivative with k. Hey, hello, come here. You haven't seen each other for a week. So here k is positive, is the growth of the population. So this is a differential equation. Okay, so to solve this differential equation, we have the method separation of variables. Can you see this clearly? You can read it? Okay. Okay. So we rewrite this derivative as the quotient of the differentials. Then we separate the p variable and the t variable. So from derivative to differentials. Then we integrate both sides. Okay. Both sides will take the integral. On the left is the integral of the variable p, even though p is the dependent variable. But after the separation, p and t, they kind of in a balanced role. This integral is with respect to p, and this integral is with respect to t. So both are integrals, but for different variables. This is for the t variable, the p variable. And now we used our fundamental theorem of calculus. We know this is logarithm. We should have another c over there for the integration constant, because we have this just represent the constant, so we can reduce them to one, just one integration constant. Another simplification, P stands for the population, so we can drop the absolute value. Then we integrate both sides. And now take exponential. Exponential we get. I'm going to switch the order. See rules for exponentials. Okay, we'll do the same trick I've used many times. Where this is a constant. The exponential of this is another constant, but it is just be positive. So we relabel this. So the solution, the differential equation. Okay, that's how we solve this differential equation. The method is separation of variables. You can separate the p variable and the t variable. So solving the differential equation becomes integrate two functions. So how to figure out this C? We use the initial condition, the initial value problem. The first one we know is the differential equation. The second one, this is initial condition. Putting them together, because there's a initial value problem. If we substitute t by 0 on both sides, so this will be p0. K0. We figure out this constant, which is given by the initial condition. Then we switch, plug in pt. So this is the solution of the initial value problem. Okay, so that's our first model is very simple. Then we make some modifications to make the model more realistic. So modify the model. Now we introduce the capacity of the environment, the container. Okay, so the maximum number of virus it can sustain. Okay. For example, if the population is less than m, that means we have room to increase. If the population already exceed m, this kind of the overcomputation, the number will decrease. So p will still increase, then p population will decrease. the two cases. The meaning of the capacity. If R, we see the derivative is positive. It's bigger than M. It's too crowded. Too crowded, then the population will decrease. So I'm not sure if you have seen this symbol before. Okay. This means we have a quantity that changes in time. This means it increase in time. It goes up. The number becomes bigger. This means the number decrease. The derivative is less than zero. Okay, so this is what we want for our model. How do we implement this in our equation? So the new model. Still okay, now let's analyze this model. If P is small, if P is very small, the derivative is approximately K P M. So it will be increase. It's similar to what we had before. Now if P is large, less than M, but close to M, this approximated M, this is M minus P, approximated zero. It's still positive, but it's very close to zero. It means the population still grows, but the speed is very slow. It grows slowly. And the third case, if the population is already greater than M, then we can see the derivative is less than zero. Okay, what does it mean, Zichen? The derivative is less than zero. If it's positive, we say it grows. If negative, decrease, the population becomes smaller because in some sense we say it's too crowded or too competitive. Uh, uh, decrease. Okay, so that's our modified model. Okay. To solve this differential equation, we use the same method, separation of variables. We put all P, this has P, and this has P. We have separate the two variables. Then we integrate. Against the left-hand side, is an integration with respect to the variable p, right-hand side, integration with the variable t. This one is a rational function. The denominator is the product. We have this partial fraction decomposition. And we get that this is solve A and B. So when P is 0, P equals M. So this partial fraction decomposition, it becomes the integral of two simpler ones. Again, because P is positive, we can drop the absolute value. So for this one, sometimes it's a positive, sometimes it's negative, it depends. We will divide this into two cases. Oh, should be negative sign. Let me correct. Minus. Correction should be minus. Um, in the case, between the capacity, when it's already above the capacity. Okay, so this is the integral of the left-hand side. This equals to the integral of the right-hand side. So we have, okay, we will focus on the case when it's between 0 and m. Again, we use the same thing with the label because they're just a constant. We can always relabel constant, but not anything else, just a constant. relabel. Now we solved the differential equation. Again, so the method is separation of variables under the assumption. Okay, so exercise for you to try is the second case. Okay, so as, what's the remaining case? The first case is less than the capacity. Second case, the bigger than the capacity. Remaining case, the same. Okay, so this is the very special case. What happens if our initial condition is exactly the capacity? Then let's check the differential equation. What's the derivative at 0? If we plug in the condition, this will be Km m minus m is 0. We don't know about the differential solution, but what we know is the derivative is 0 at this time. And then we can check a new notation. Okay, who had seen this notation before? Triple bar. Elisa, have you? Okay, Sophia, no.
Yeah. Is it congruent?
Okay, so this one, in different contexts, has different meanings. In number theory means modular, but in function theory, that means it's equal for all t. Okay, so in number theory, means something else, but in our case, functions. It means pt equals m for all t. Okay, now let's want to check if this constant solution, constant function, is a solution of the differential equation. Okay, question, how do we check? Sophia, what would you do? is this a solution of the different equation? Elisa, what would you do, Elisa? Okay, Zicheng. No. Sakina, you know.
What would I do?
So now we have a differential equation. We have a function. We want to check, is this a solution? What we do is we plug this into the equation. But under this one, we just plug in. This one, we find the derivative. Because first, what's the derivative of this function? Y. It's a constant. Okay, so that's easy. It's not difficult. So check. So how to check? The derivative is 0 because it's constant. Now we plug this into the right side of the equation. Okay, it's identity m minus m also 0. Okay, so left side, right side, both 0. So this means this is a solution of different equation. Okay, it's a solution, but it's a constant solution. Okay, for the previous solutions, if we go to the previous page, the solution is a function. Sakina, let's get back to class. Okay, okay.
I want to get a like right now. I'm sorry.
Okay, okay. So normally we expect the solution of a different equation to be a function that changes in time. But in this case, we have a very special one. It's not changing at all. Okay. So we give it a special name. It's constant solution, but we call it an equilibrium solution. A new term. Okay, who has seen this term before? Equilibrium. I think you maybe heard of it. Okay, physical meaning in physics. Okay, okay. So it means something in a balanced state. It's not moving left, not moving right. You stay put. Okay, okay, okay. Maybe it's the same thing. It's equilibrium. So like what our function have, is stay at m, not increasing, not decreasing, but constant. Okay, okay. Let's start another model. Another model, the mass spring system. Okay, who had heard this before? Mass spring. Maybe, okay, you said you something in physics. Maybe Elisa, have you heard of this before? Mass spring system.
Mm, yeah.
Okay, what's it about?
Um, you have a mass on the spring.
Uh-huh. Okay, okay. So there are different ways to describe this mass spring system. One is vertical, one is horizontal. I'm going to choose the horizontal one. So that's the setup. Then we have a spring. Okay. Okay. Now we have a box. Oops, not. Ah, that's good. We know this. Okay. So we assume the surface is very smooth. In particular, there's no friction at the moment. Then this box, if the spring is relaxed, the box is not moving left, not moving right, it stays there. We call it an equilibrium, in a balanced position, not moving. Now, let's see, very simple physics. If we pull this box over here, then we release it. So okay, now what happens if we release the box over there? Bounce back and forth. Okay, okay, that's enough for physics. Okay, if we pull it to the right, then release, it will contract, but it will move a little bit to the left, then push back, so it bounce back and forth. Okay, that's the first scenario. Second scenario, if we push this to the left, then release, then what happens? Okay, it's a bounce back, then back and forth. Okay, so that's the physics. Now we want to give a mathematical model for this. We want a model how this changes in time. Again, there are different models. We will start with the simplest one. The simplest one is that if we have a displacement, zero, x. Okay, so if we have a displacement from 0 to x, then the force of the spring is proportional to the displacement. So that's the first assumption. The force of the spring proportional displacement. And it's in the opposite direction. If we pull the spring, spring will give us pull back. It's in the opposite direction. Okay, so this way, a second thing we need is Newton's law of motion, the second law. is the acceleration. F stands for force. M is the mass of the object. A is acceleration. Okay. Yeah, since if there's no force, then there's no acceleration. It moves at the constant speed. If we have a force in the same direction as acceleration is positive, force in the opposite direction of deceleration due to the law of motion. In the first assumption, F in our case is proportional to the displacement. But in the opposite direction. So we write the equation. So K is a positive constant, the proportional. And we put a negative sign over there to indicate it's in the opposite direction. So we will call this K spring constant. Because for some spring, this K is very large. Because if we have a very strong spring, a little bit of pull or push, we create a very large force. But some spring is not that strong, so K will be small, depending on the spring. Okay, so how do we model this acceleration? If we have the position at time t, how do we find the velocity at time t? Sophia, what's the velocity? Sophia has been quiet the whole day. I'm not sure if her mic works. Sophia, can you hear us? I think you can hear, Sophia.
Yeah, I can.
Okay, so now if this is the position at the time t, how do you find the velocity at time t? So
Do you take the derivative?
we take the derivative. Okay, so in physics, the physicists, they want to save space for this particular case. Instead of prime, they invented a system language using this dot. Okay, to you, there's no difference. You put the dot, it's one more stroke. You put a prime, it's one stroke. It's the same thing. Didn't save anything. But the advantage of this, if you want to write a square, so r prime, if you write a square directly, this looks strange. Normally, we would have to use this r prime square. But if you use dot, then square. So there's no ambiguity. We take the derivative, then we take a square. In physics, they have systems. So the physicists, they deal with the derivatives all the time. So they invented this treatment. Okay, so we will use this when our independent variable is the time. When we take a derivative, we can put a prime, or we can also use the dot. So Kenda, do you agree? Okay, okay. Okay, so Zichen, what's the velocity acceleration in terms of velocity? If we know the velocity, how do you find the acceleration? You take a derivative again. So we take a derivative of the velocity. Okay, so velocity is already one derivative. The acceleration will be the derivative of the derivative will be the second derivative. Again, physics notation. Notation will be double dot. Oh, it's not R. Okay, so position, velocity, R dot, acceleration, double dot. In this equation, we have the acceleration, and we have, okay, I used X. Okay, let's combine them. Let's switch to X. I'm going to unify is our notation. X looks strange, but it's X. Okay, so now we have the differential equation. F equals ma. A is double dot, second derivative. Okay, X. Okay, so this Newton's law of motion, and this the spring property. So this is our second. We call this the mass spring equation. Again, it's a differential equation. Compared to the previous one, this is a second order differential equation because we're taking the second derivative. Okay. So now we can see how this differential equation help us solving or at least modeling the behaviors, the phenomena in our real world. We have the population model, and we have this mass spring model. We have the different equation. Now, from a physics problem to a mathematical problem, how do we solve the different equation? That is a mathematical problem. Okay, so to solve this different equation, now we briefly mentioned this method of separation of variables. Now we have more about this. Separation of variables. We deal with the general case. Let's have 5 minutes break. After the break, we discuss the general case for this separation of variables. Okay, be back at the 50. Okay, so now we give a systematic treatment of this method, the separation of variables. We consider the following general form of different equation. This is an explicit first order differential equation. For comparison, in the future, you will learn the implicit. An example of the first one. Example of the second one. The first one, the derivative, depends explicitly on the function. So it's explicit first order differential equation. This one, the dependence is implicit differential equation. Okay, so this method of separation of a variable applies if we can separate the x and the y in this function. So take a seat, take a seat. Okay, so the differential equation. We say it's separable if this function is the product of two functions. One is about x only, and the other is about y only. If we can separate the two variables, x and y, on this side, then we say this differential equation is separable. So for this type of differential equation, we can apply the method of separation of variables. Let's check y derivative sine x. Well, is this separable or not? Could we write this as the product of two functions?
Yeah.
One,
Wait.
okay, so how?
No.
Okay. I have one answer says no. So this is not separable. We cannot write this as the product of two functions. Next one. Is this separable? Sakina, think about the question.
Ew.
Okay.
Yeah.
Okay, I have some answers. Okay. Why?
Because you can do e to the x times e to the y.
Okay, now see, both are x plus y, but this one uses the property of the exponential. Yes, the exponential property, e to the x, e to the y, and that's what Sophia also mentioned. Okay, so that is separable. Okay, for separable differential equations, let's see how to solve this. dy over dx equals fxy, and it's separable gx hy. Okay, so we will separate, put y on one side, x on other side. Then we separate the two variables. dy. Okay, now we separate them. Then we can take an integral. Remember, when we take an integral, we have to specify what variable are we integrating. Okay, so on the left, we integrate the y variable. On the right, we integrate x variable. Okay, let's see. Let's try this one. It's separable. Okay, let's separate the two variables. See what you get. Y derivative. Okay, how do we separate them? Okay, so first step, from derivative to differentials. Then, okay, Zichen, next. So how do we, so from here to there, how do we separate x and y? I divide the part of y from both sides. Then I move dx to the other side. Okay, so this will be, okay, and this 1 over is the y. So by our exponential property, we just simplify it. 1 over is the y. Could you simplify this? This will be e to the something. Negative y. Okay. Then we integrate. So e to the negative y dy integrate. Okay, let me rewrite this part. This is easy, ex plus c. What about this? Elisa, how do you integrate this?
E to the oh yeah.
And is this all, or do we need to make some adjustment? If we take a derivative, what do you have? We apply chain rule, it will be e to negative y, negative 1. Derivative is just negative 1. It will be negative 1. When you cancel this negative, we put a negative. That's the integral. In this way, we have the solution. So let's get rid of the negative. So e to negative y, negative c x. Again, we relabel the constant because it's just a constant. Relabel. Well, okay, so in this formula, c stands for integration constant. Maybe 1, maybe 2, maybe 5. It could also be negative 1, negative 2, negative 5. It's just stand for a undetermined arbitrary constant. Since it's arbitrary, the negative c also stands for an arbitrary constant. If c is 1, this will be negative 1. C is negative 1, this will be 1. So negative c and c, they play the same role.
I just said, why did you relabel it? Yeah.
So because in the process, like what I've done before, we want to make the formula as concise as possible. This negative c and c, they represent the same thing.
So what did you see?
Relabel this whole negative c to a new c, a different c. Okay, okay, let me write this down and I will tell you what's the difference. Okay, so this c is an integration constant. This c also stands for integration constant. The difference between them is when we choose 1 here, we choose negative 1 for this. If I choose negative 1, this negative 5 for this c, I choose 5 for this c.
So relabeling, dude, I'm like so confused.
It doesn't do much. It doesn't do much. The only thing is, do you prefer this equation or do you prefer this equation? Basically the same, yes. It's just a name. You call Sakina, I mean, you call Zichen. If I switch Zichen, Sakina, what does it change? Nothing. It's relabeling. That's the same thing. I just change the name, but because they represent the same thing. You still her, but just the relabel. I relabel this Zichen. Okay, nothing big. Not so. That's why we are allowed to do it. What's that?
Nothing, sorry.
Because nothing essential changes, just the name. Nothing essential changes. Otherwise, we cannot do this. If this is 1, this is 2, we cannot do it. Only change the. So you can see I. Yes. That's the only purpose, to make the looks better. And it doesn't change any essential aspect of the equation. Otherwise, if let's say if I multiply by 2, then we will compute different equation. I cannot do that because it changes the things essentially. But this one, nothing essential.
Yeah.
Okay. Okay, now let's have something more challenging.
Oh.
Let's-
No.
okay. 6x squared.
I know. You started it.
Okay. Settle down. Okay. No. Okay. First, let's check this. Looks okay, intimidating. How do we integrate this? Well, step by step. Is it separable? That's the first question. Okay, how? How do you separate them?
Oh wait, it has to be times. Okay, sure.
So it's S, no, sorry, GX HY. Okay, the good news is, even though it's complicated, but it is separable. It's separable. Now let's start the work. So dy dx 6x squared. Okay, Sophia, how do you separate this equation?
You take the derivative.
No, separate. So like what we did have done over there. So if the function is the product of x and y, how do we separate? We divide, we move the term y to one side and term of x to the other side. After the separation, this side, no x. This side, no y. So x and y, they are separated. That's the separation of variables. So here, how do we separate x and y?
You multiply dx.
Mm-hmm. And what about this part?
And then you multiply by 2y cosine y on both sides.
Okay, so now we separate. So it'll be 2y cosine y dy 6x squared dx. Okay, Elisa, it's separated. What's next?
Take the integral.
Yes. Okay, now from a different equation, so one different equation, two integrals. Okay, now it's Sakina. What's the integral of this one? Which is, so first, what's the power? Integral or derivative? What's the integral? Antiderivative.
Sorry. Oh.
2x. That's what you said? 2x cubed? Oh, that's correct. That's correct. Okay. I misunderstood. Okay. Sorry. Okay, and this side. Okay, so the integral of addition is addition of integrals. Okay, Sakina already found this. Again, we have the integration constant, but we can only keep one of them. Now our solution is this is an implicit solution. The dependence of y on x is implicit, the implicit solution. This method, the separation of variables, often give us an implicit solution because we cannot control what the integral give us, something maybe complicated. However, you can see this different equation looks scary at the beginning, but we recognize it's separable. It's separable after the separation, that becomes two integrals. Then we have done so many integrals, these are not difficult at all. So one different equation, if it's separable, two integrals, one about y, one about x, we get an implicit solution. Okay. Let's try another example. I'm going to make something. Is this okay? Let me just think about it. Maybe it's 5 ways better. Okay, let's try to solve this different equation. Okay, whose turn? Okay, Sophia. Is this separable?
Yeah.
Okay, it's the product of x term with y term is separable. Now we will separate the two variables, dy. e to the Okay, Zichen, what's next? What's the steps? Not the result. What's the next step after we separate the variables? The integrals. We do them one by one. Integral of summation is summation of integrals. It's again the first one, sine x. Okay, and Elisa, logarithm
1 over x.
as the derivative. What method we need to find this one? He's thinking.
Oh,
Yeah. So to integrate this one, the formula doesn't work. We have to use this integration by part. So it will be, we put a 1 over there. This will be f g derivative. Integration by part that gives us okay, I have done it, so I will skip the process. And Sophia, how do you integrate this one? Again, we need to simplify this. We use the property of the exponential. This will be e to the 5, e to the 1. Maybe we just flip it. Easier if we just flip everything. E to the negative 1, 5d1. If we integrate this, it will be negative. Okay, so put them together, we get the solution of the different equation. Little bit complicated, but the steps, they're not that difficult. So separation of variables, integrate both sides, then we get the solution. Okay. Then there's another type of the first order differential equation. We call it linear differential equation. Very important. Okay. We could, okay, that's another thing about the relabeling. We could have, that's a very good point. Let's spend a few minutes over there. We should have one constant and another constant. That's what we should have. This integral gave us one constant. This integral gave us another constant. Oh, now this should be C1 minus C2. Okay, this is a constant. Label the whole thing as a one constant. Yes, now you know the trick, how we play this game. Okay, so the only achievement with this relabeling is to make the formula simpler, but without changing anything essential. The same thing just with this simpler notation. Okay. linear. Linear differential equations. And in many books, they often omit this differential. They just say linear equations. It has a very special form. Y derivative. If it's this form, let's see an example. How to solve this different equation? Let's check if our old method works. Let's check what derivative cosine x. Is it separable? Sophia, what do you say?
Mm,
We
I
can
don't
try
think
it.
so.
It's not easy, so it's not separable. Okay, so the only method we know up to now doesn't work. So another method is we want to try to make this side something we can apply this fundamental theorem of calculus. If we can write this as the derivative of something, I don't know what it is, then the fundamental theorem tells us this thing will be the integral. The fundamental theorem of calculus. To make this derivative, it's not something derivative, it's y derivative plus xy. So we want to make it like something, so fx, if we apply the product rule, we get fx y derivative, f derivative 1. Okay. What's missing, if we compare what's given and what we want this to be the derivative of something so we can apply the fundamental theorem. Compare with this, we can multiply this by f to make the derivative of this. Okay. Compare with, so this will be fx y derivative. We compare with okay. Now our task changes. We wanted to apply the fundamental theorem of calculus. If we can find a function whose derivative over f itself is x. Okay, so a slightly easier task. Could you think of something whose derivative over itself is x? Not easy. Not easy. So now we integrate both sides because this is a separable equation about f and x if we integrate, this will be df over f x dx. Okay, separable logarithm. We assume it's the positive, so logarithm f 1/2 squared. Okay, so we pick because we just need one function. We're not looking for the general one. Fx will be exponential. Okay, now let's check this function. What's the derivative? Okay, so Jane and Sakina. And Sophia and Elisa. This function, what's the derivative?
It's
Time.
x.
Okay, I heard someone say x. This is the derivative of this. Now you can see if we divide by f, we divide by, we get x. Okay, so now to apply the fundamental theorem of calculus, we will multiply both sides with this f. Then this will be the f time. Okay, so let me step by step. We multiply both sides by this f. I had cosine x. This gives us f x y derivative x f f x x y. And this we know is f derivative. So this is the product rule. Now we are ready to apply the fundamental theorem. Fx so the solution is 1 over fx cosine x dx. Okay, so we haven't finished the integral, but we reduce the problem from solving this differential equation to the integral of some function. So we treat this as a progress. If we convert a difficult problem, solving a different equation, to something simpler, in this case, the integral. So it's a progress we made in that direction. Okay, we'll have more examples of this next time. Okay, any questions? Okay, and the two of you, Sophia and Elisa,